Hi, Jim Heffron. These are my lessons in Calculus 1 and getting down near the end here. So we're doing the homeworks for the method of shells. We're finding volumes by method of shells. And of course, as always, we'll start off by going back and picking a section from, a week ago, 2 weeks ago, maybe a month ago. In this case, we're doing one problem from section 5.5. Okay, let's get started. So let's see. The textbook is, of course, the Stewart textbook. Give credit where credit is due. Is the Stewart textbook, which is a good textbook. There are other good ones, but it's a good one. So I am doing evaluate the indefinite integral, and it's the integral of x square root of 1 minus x squared dx. Okay, so picked kind of a typical substitution problem. Okay, so let's see. So the integral of x times the square root of 1 minus x squared dx. All right, and as always with substitution, a person thinks here that there's some kind of composition involved in this expression, so that makes us suspect that it might be substitution. Good. Also, it's in the substitution section. But anyway, if you weren't in that context, you'd say, well, there's a composition, so maybe substitution. And so you think the 1 minus x squared is being square rooted, so that suggests that it is u. So du dx minus 2x. So that du is minus 2x dx. And I, of course, was given an x dx, not minus 2x dx. So I end up with minus 1/2 du equals x dx. And that's what I was given, so I'm happy with that. So we end up with the substitution. We're looking at square root of u times a minus 1/2. And then a du. Bring the minus 1/2 out. U to the 1/2 power du. So we've done the antiderivative of u to the 1/2 many times. So minus 1/2. We get here to 2/3 u to the 3/2 plus capital C. That minus 1/2 doesn't look so great. Plus capital C. And I'm going to go back and replace the u with what u equals because the question was originally asked in terms of x's, so it's polite to answer it in terms of x's. So I get minus 1/2 times 2/3, the 2's cancel, and I get minus 1/3, then 1 minus x squared, quantity to the 3/2. And when you take the minus 1/2 and multiply it by capital C, the convention here is that you have an unknown constant and you multiply by minus 1/2, you get another unknown constant. And so we write that as plus C. I know that's a little bit not right, but that's the convention. Okay? Okay, great. So now we turn to section 6.3. I've only listed here 3 problems. It's been my experience that sometimes when folks do these, they have a little trouble with the 3D stuff. Just getting used to 3D stuff, that's all. And so I think they can sometimes take a little longer. All right, so let's look at the first one. I just picked number 1 because I tried to pick a bunch of different kinds of problems. There we go, got it on the screen. It says let S be the solid obtained by rotating the region shown about the y-axis. So we're spinning that about the y-axis. Explain why it's awkward to use the washer method. That is to say disks to find the volume of S. Then it says do it with shells. Okay, so let's have a look. I have a graph of, too much stuff. I have a graph of x times x minus 1 quantity squared. And they drew a picture, so they got some kind of thing that looks like this. This is x times x minus 1 quantity squared. And I'm interested, this is supposed to be 1. And this is 0, obviously. And I'm interested in explaining why, first of all, why disks would be awkward. So if I were to do this, well, first let's spin it about the y-axis. I'm a terrible drawer, but anyway, just to give a spin it about the y-axis. There's the y-axis coming up through the middle, and of course it curls in a little bit and it tails off a little bit. Okay. Okay. So the difficulty with taking a slice here, if I tried to take slices dy, is figuring out what the two ends are. So if I try to take slices dy, then I got to figure out what the two ends are. So I have to solve. I have to solve for y there. To express x in terms of y. So I'm looking at the y equals x times x minus 1 squared. And this is going to be a cubic. So I have to solve a cubic to get y equals, some expression of y equals x. And so that's going to be hard. I mean, sometimes you just look and say, well, I can see that the answer is, but it looks to be awkward. So instead, if we do shells, oh, I didn't quite make the y-axis below. Anyway, I did what I did. If we do shells, then I have a shell like so. And it's easy to express. That's going to be x times x minus 1 quantity squared. And when I spin that about the y-axis, I get a shell that looks like so. Okay, so I think that looks easier. And I'm going to set up, but I'm not going to solve it. So I get the integral from x equals 0 to x equals 1, because that's what the picture says. The smallest such x is 0 and the largest such x is 1 of, let's say, if I cut that shell out and laid it flat, it would be x times x minus 1 quantity squared tall. It would be 2 pi times x long, and it would be dx thick. So 2 pi x times x minus 1 squared, and then times dx. Okay, and a person can say, well, I don't see how to do it, but you do see how to do that right away, because this is a polynomial. It's a bunch of x's. You multiply them all out, and you get something easy to antidifferentiate. So I'm just going to go that far, and I'm not actually going to antidifferentiate from 0 to 1, bring the 2 pi out, and I'm looking at x squared times x squared minus 2x plus 1 dx. And actually, maybe I'll stop there, because clearly what you get here is a polynomial, and antidifferentiating is going to be easy. Plug in the 1, plug in the 0. Don't forget to multiply by the 2 pi. Okay, great. So that was number 1. Next up is number 5. Let's see if I can get that to the. There we go. Number 5. It says, set up but do not evaluate an integral for the volume of solid obtained by rotating the region bounded by the given curve about the specified line. And of course, I'm going to do this by shells. Of course I am. So it says y equals ln of x, y equals 0, x equals 2 about the y-axis. Okay, so y equals ln of x. We've done ln an awful lot in the course of the semester. Ln x. That's the point 1, 0. And this is going to be 2. And so this, of course, is going to be the point 2, ln 2. 2, ln 2. And that must be the region of interest. We're spinning it about the y-axis. So when we spin it about the y-axis, we get something that looks like so. And it curls in, and if you had X-ray vision and could see to the center, you could reach your finger in the top there and almost touch the bottom. Okay, so it seems to me that if I take a shell, I'm spinning it about the y-axis, so shells are d something other than y, so dx in this case, obviously. If I take a shell, then it would look like so. And when you laid it out flat, you cut it and laid it out flat, it would be 2 pi x by ln x by dx. Okay, so I'm looking at the integral from the smallest sensible x to the largest sensible x. Well, when you look at the slices, the smallest x can be 1. The largest x can be 2. 2 pi x ln x dx. Obviously, a person would bring out the 2 pi. And we find ourselves trying to figure out what is the antiderivative of ln of x times ln x, and it might not be obvious to you right away. You might remember it, we saw it early in the semester, but I'll note that it involves a product of two things, and so it suggests that what you need here is a version for antidifferentiation of the product rule. And that's one of the first things that gets tackled in calculus 2, so not here. Anyway, the problem said set up but do not solve, and I've set it up but did not solve it, so I'm done. Okay, great. And then the last one, again, I'm only doing 3 problems in section 6.3 because it has been my experience that people take a little longer on these, so you would use up the whole Pomodoro because the 3D is new to folks. So just a lot of people spend time going, what happens over here? Oh, wait, let me figure it out, sort of stuff. So number 9 says, use the method of shells to find the volume generated by rotating the region bounded about the y-axis. So square root of x, y equals 0, x equals 4. Okay, so I'm looking at y equals square root of x, y equals 0, and x equals 4. And we're looking at about the y-axis. Just because they told me to do about the y-axis. This is number 9. So we have a good idea what most of these look like. We spent a lot of time practicing drawing graphs, and so we get a pretty good idea. See if we can get the region here. Square root of x looks like so. Familiar formula. X equals 4. So this, of course, is going to be the point 4, 2. Y equals 0 is the x-axis, and so I think we must be interested in this region here. We'll give it the measles. Interested in that region there. I'm spinning it about the y-axis, so I get a shape that looks like so. Like so. Okay, getting faster at these. So spinning it about the y-axis, so shells is anything other than dy. There's only one other variable here, so I must be doing dx. If I cut it open and laid it out flat, that fellow would be square root of x tall, 2 pi x long, and dx thick. Okay, so setting up the integral, I get here, oops, maybe a little up. Setting up the integral, I get the smallest x to the largest x, so x equals 0 to 4. 2 pi x times square root of x times dx. I'll bring the 2 pi out, 0 to 4. Let's see, this is x times x to the 1/2, so that's x to the 3/2 dx. Just to go on, just to finish, although really I'm at the it's all easy now point. The antiderivative of x to the 3/2 is some kind of 2/5 x to the 5/2. So some kind of 5/2. Plug in 0, plug in 4, and plug in 4, plug in through 0, and then subtract. So what I get is I'll bring the 2/5 out just to get it the heck out of there, and there's a 2 pi. And I'm looking at 4 to the 5/2 minus 0 to the 5/2. Okay, and then let's see, 2/5 times 2 pi makes a 4 pi over 5. 4 to the 5/2, we've talked about this before. There's two ways to do that. You could raise 4 to the 5th power and then find the square root, or you could find the square root of 4 and raise that to the 5th power. So, you figure out which is easiest. So I'm looking at 32. And you could go on to multiply 4 by 32, but maybe I'll stop there. Okay, very good. So again, the lesson here is that we could have decomposed this into discs, what the book sometimes calls a washer because it's got a hole in the middle. We could have decomposed it into discs by taking the slices that are dy thick. Fine, but we did it a different way. So we decomposed the region into these shells and got going to be the same answer, got the answer with shells that way. So integration is about accumulating together somehow this decomposition of the region into these infinitesimal volume areas. And again, making the point that integration is not about volumes per se. Integration is about accumulating continuous quantities. We happen to be accumulating the continuous quantity of volume because it's easy to draw and a person can see what's happening and get a good idea of where we're going. All right, very good, very good.